Exothermic and endothermic. Exothermic reactions release energy to the surroundings, so the temperature rises. Combustion, neutralization, and hand warmers are all exothermic. Endothermic reactions take energy in from the surroundings, so the temperature falls. Thermal decomposition and sports injury packs are endothermic. The clue is in the temperature change. In an exam, if the question says the temperature of the surroundings rose, then the reaction is exothermic. If the temperature fell, it is endothermic, and the temperature change is the giveaway. Reaction profiles. A reaction profile is a graph of energy against the progress of a reaction. For an exothermic reaction, the products are lower than the reactants on the energy axis, and that's because energy has been released. For an endothermic reaction, the products are higher, because energy has been absorbed. Both graphs have a hump in the middle, and that hump is the activation energy. Always label 3 things on a profile: reactants, products, and the activation energy. Lots of students forget the activation energy label and lose an easy mark. Activation energy. Activation energy is the minimum energy needed for a collision between particles to actually result in a reaction. A higher activation energy means a slower reaction. A catalyst speeds the reaction up, not by changing the temperature, but by giving the particles a different pathway with a lower activation energy. The catalyst itself is not used up in the reaction. In an exam, never say a catalyst lowers the temperature or speeds the particles up. The correct phrase is provides an alternative pathway with a lower activation energy. Required practical, temperature change. For the required practical, you measure temperature change for a reaction, like hydrochloric acid plus sodium hydroxide. You use a polystyrene cup because it insulates well, and a lid to reduce heat loss. Record the starting temperature, mix the reactants, then record the maximum or minimum temperature. Plot temperature against the volume of one reactant added, and the peak shows the equivalence point. In an exam, the 2 marking points for why a polystyrene cup are it's a poor conductor, so it reduces heat loss to the surroundings. Saying just it's plastic is not enough. Making water potable. Potable means safe to drink. In the UK, tap water starts as fresh water from rivers, lakes, or reservoirs. The process has 3 steps. 1. Filter the water through beds of sand and gravel to remove solids. 2. Sterilize the water using chlorine, ozone, or UV light to kill microbes. 3. In some places, add fluoride to protect teeth. If fresh water is scarce, seawater can be made potable through desalination. Distillation boils the water and condenses the steam, and this leaves the salt behind. Reverse osmosis pushes salt water through a partially permeable membrane. Both desalination methods use lots of energy, which is why they're mostly used only where fresh water is genuinely limited. In an exam, the marking points for fresh water are filter, sterilize, sometimes fluoridate. For seawater, it's distillation or reverse osmosis. Reversible reactions and equilibrium. Some reactions can go both ways. The reactants form products, and then those products can break back down into reactants. We show this with a double arrow. If a reversible reaction happens in a closed system where nothing can escape, the forward and backward reactions eventually reach the same rate. That's called dynamic equilibrium. The amounts of reactants and products stop changing, but both reactions are still happening underneath. In an exam, if asked what dynamic equilibrium means, the marking points are forward and backward reactions at the same rate in a closed system with no overall change in amounts. The Haber process. The Haber process makes ammonia from nitrogen and hydrogen. Nitrogen comes from the air and hydrogen from natural gas. The reaction is reversible. Nitrogen plus hydrogen makes ammonia with a double arrow showing it can also go backwards. The conditions are around 450 degrees Celsius, 200 atmospheres, and an iron catalyst. These conditions are a compromise. High pressure pushes the equilibrium towards ammonia, but that's expensive. Lower temperature also favours ammonia, but slows the reaction. The chosen conditions balance yield against cost. Ammonia made by the Haber process is used mostly to make fertilizers which help crops grow. Life cycle assessment. A life cycle assessment, or LCA, looks at the total environmental impact of a product from start to finish. It covers 4 stages. 1. Getting and processing the raw materials. 2. Making the product. 3. Using the product. 4. Disposing of the product. For each stage, you consider the use of natural resources, the energy needed, the waste produced, and the pollution caused. LCAs help us compare different products fairly. For example, comparing paper bags to plastic bags isn't as simple as it sounds. Each has different costs at each stage. Recycling reduces waste and saves energy compared to making new products from scratch. But recycling itself uses energy and produces some emissions. That's why a full LCA is needed to judge the real impact. And that's it, your Edexcel Combined Science Chemistry Paper 1. I hope you found the video useful and good luck in your exams.